I warmly welcome you to the long oral here at UNSURE about Reversible PHiSeg. It's a memory-efficient neural network architecture for the quantification of segmentation uncertainty in medical images. My name is Marc Gantenbein. I did this work together with Ertung Erdil and Ender Kunukoglu at the Computer Vision Laboratory of ETH Zurich. Medical image segmentation is usually about finding a mapping F from an input image to a segmentation. So in the medical domain, maybe we're given an image of a CT scan or something similar, and we want to find a certain region of interest. This could be a lesion or a tumor or an anomaly that we want to detect and should be done computationally. So we would then look for a mapping from this image to a segmentation. However, when we now do this by hand, let's say we give an image to various experts to do the annotation for us, for example, finding a tumor or something like that, we usually end up with different segmentations. And when this is done automatically, we sometimes also want to access multiple segmentations at one to choose from them. So the solution to this is generative modeling, or one of the solutions to this is generative modeling. It can deal with the inherent ambiguity of the segmentations and allows us to have multiple segmentations. For generative modeling, we treat the likely segmentations as samples from a probability distribution and not as the output of a deterministic function. So for this purpose, we can assume a graphical model with latent variables. These latent variables define the behavior of our segmentations. So this graphical model with these latent variables has found application for variational autoencoders. They're based on variational inference. And the combination of the Unet, the neural network architecture for generating segmentations, with a conditional variational autoencoder has led to the famous architecture Probabilistic Unet. The Probabilistic Unet is an architecture that offers us the possibility to sample different likely segmentations for the image that we feed into. So for the inference part in the network A, we have the encoding part of a variational autoencoder, and this encodes our image to a latent space, and we would then feed the image into our Unet architecture and append the latent space to the Unet architecture. We could then sample from this network by just sampling from the latent space, and we would thus obtain different likely segmentations. A direct extension of this network is the PHiSeg architecture. Here we also have the Unet-like structure of the probabilistic Unet shown before, but instead of sampling the latent space and appending the latent space to the end, we would just sample on the latent levels of the Unet architecture. So what was then our work? As you might guess, these probabilistic hierarchical architectures have a significant memory consumption. So usually when training and experimenting with them, one ends up with the following error. So our goal was to employ memory saving techniques that do not incur any performance loss. So we have the same performance as before and can be easily integrated into various architectures and do not change the convergence behavior or something similar. So the questions we set out to answer were if we can use less performance while achieving if we can use less memory while achieving a similar performance, and can we process bigger batch sizes and do we gain any advantages from it? And can we process a larger resolution to obtain better segmentation performance to make our samples even better? So the concept we wanted to employ was the reversible blocks. The key concept is that instead of storing the activations during the forward pass, we we just pass our image through these blocks. And then for the backpropagation, where we need the activations, we would recalculate them by doing the reverse operation. It's a concept introduced by Gomez in 2017 and has found applications in different architectures so far. So there's a direct trade-off between memory and training time due to this recalculation. And it's similar to gradient checkpointing, but there's no reordering of backward and forward computations, and we do not have to have any knowledge about the computation graph, so about the order of the operations. And it's more, for the reversible blocks, we just have to replace these blocks with the reversible blocks. To present an example, I have here 3 convolutional layers in a row with a 3x3 kernel, could be another kernel as well. And during a normal forward pass without reversible blocks, we would just store the activations after each convolution. And then for the backpropagation, we would fetch the activations for the convolution and do a backpropagation algorithm for the layer. Now with reversible blocks, we would just pass these through our reversible blocks, the images or the activations, and then after the reversible sequence, we would store them. For the backpropagation, we would then fetch this stored activation and recalculate all the activations that we need for the backpropagation. The integration of the reversible blocks into our network is done by dividing the input of our function, for example, the convolution that I already presented, into 2 equal-sized parts. Equal-sized parts can be done by channels or by height and width. They just have to have the same size. The forward and backward pass would then be calculated as following. We have the forward pass where with the 2 input parts, and there's 2 addition blocks. And for the backward pass, we would exactly inverse this operation. As you might guess, the constraint here is that we have to have the same input and output dimensions, since if this is not the case, the inversion would not always be possible. So for 3x3 convolution, if we have less channels, for example, we go from 64 to 32 channels, this would not be possible. So we could not replace this convolution with a reversible block. If we have the same number of channels in the input and the output, we can do it. So we can replace the convolution with a reversible block and with the which I presented before. So when considering the PHiSeg architecture, which we wanted to make more memory efficient, stated in the beginning, we have to look for blocks where there are multiple convolutions in a row. And here we have multiple 3x3 convolutions. However, they always feature a downsampling step, so we have a dimension change. How do we deal with this dimension change? We have this sequence here where we start with, for example, 64 channels and go up to 128 channels, as in the downsampling path of the PHiSeg architecture. And what we did was we appended a 1x1 convolution that did this channel increase. And then the 3x3 convolutions always had the same channel number at the input and output. We could then replace all these blocks with reversible blocks. So during the forward pass, we didn't have to store any activations in this sequence of 3 convolutions. Here, a graphical view, as you see, you have the 3 convolutions in a row, and then the replacement of the addition of the first 1x1 convolution to have the same input and output dimension for the reversible sequence. For the PHiSeg architectures, this then looks like the following. We have our original architecture, and this is the reversible variant. So as you can see, all the sequences of convolutions are replaced by these reversible sequences. How did we validate our architecture? The experimental setup we had was to repeat the experiments as given in the original PHiSeg paper. We compare the PHiSeg and reversible PHiSeg on the LIDC and UCH prostate dataset. And we evaluated the same scores as in the original paper. We logged the memory consumption to see if we indeed have any memory advantage and trained them for 48 hours, as was done in PHiSeg as well. The experiments were additionally performed with different batch sizes and different resolutions for the UCH dataset, and the experiments and architectures are publicly available on GitHub. So the datasets, the LIDC, the Lung Image Database Consortium, also introduced by Armato. It consists of lung CT scans with 4 annotations, and there are 2 classes. The UCH dataset is an in-house dataset. It's downsampled from 512 to 512 pixels, and there are 3 classes with 6 annotations. The metrics we evaluated were the generalized energy distance. It yields us a single number to quantify the distance between the 2 probability distributions. So it's a number for the sample quality. How good are the samples? How similar are they to the ground truth samples? The average normalized cross correlation. If we do not average over all pixels, there is an individual value for every pixel linked to the cross entropy. So we can see where our samples are worse than others or worse than ground, are not very good. And to account for plane segmentation performance, we evaluated the DICE score. The results we obtained are the following. So we have here the results for the LIDC dataset with different batch sizes. And as you can see, the original PHiSeg is slightly better in terms of the generalized energy distance and the average normalized cross correlation. So the sample quality is a bit higher. However, for plane segmentation performance, the reversible PHiSeg outperforms the original PHiSeg. This might be due to the additional 1x1 convolution that we introduced for dimension change. And since we have more parameters, the segmentation performance might be better due to this fact. The memory consumption is always about around 25 to 30% lower, and the performance does not differ by much. For the UCH dataset, we can observe a similar phenomenon. We have a better generalized energy distance and a better normalized cross correlation. Here, the DICE scores are about even. There's a slight difference, but not by much. And the memory consumption is also around 30% lower. What is interesting to note here is that the higher resolution we processed with the reversible PHiSeg was much better. And we weren't able to repeat the experiment with PHiSeg due to memory constraints. So with PHiSeg, we ran out of memory for this architecture. So to come back to the beginning, we set out to answer the following 3 questions. If we can use less memory while achieving a similar performance for this generation of samples, of segmentation samples. And we can clearly state yes, although we are like a little bit worse, the sample quality is still very good. And the batch sizes, the bigger batch sizes we processed didn't prove to be of any advantage. And the resolution, the higher resolution we processed proved to be beneficial in terms of the generalized energy distance. So the sample quality increased since we were able to process a bigger resolution. To give a short outlook of our work, this technique we employed also allows for the extension of probabilistic Unet architectures, so probabilistic Unet and PHiSeg to 3D datasets. We didn't perform any experiments in this direction since we didn't have a suitable dataset available. And a next step will also be to integrate other memory saving techniques, such as gradient checkpoint, to see if we can even perform even better. I'd like to acknowledge the support of the ETH Zurich for the resources and locations for doing this work, and its project Personalized Health and Related Technologies for funding, and the NVIDIA Corporation for hardware in the form of GPUs. And I'd like to thank you very much for listening to this talk, and if you have any questions, feel free to ask them.